Slonche. Well, honestly, that is the only Irish word that I can think of right now. I've been to Ireland, but I found out that that's how they say cheers. Like, you clink a glass, you say cheers. They say slonche, which kind of reminds me of a combination of cilantro and lawn chair. But anyway, I'm making this video on Valentine's Day, so it's an Irish holiday. So I wanted to say Happy Valentine's Day, or not Valentine's Day, St. Patrick's Day. Say Happy St. Patrick's Day. Um, this lesson is going to be about similarity transformations. We did a lesson on congruence transformations, but now we're going to do one on similarity transformations, and how you can combine transformations to show that things are similar. And it's really going to be a piggyback off of last section on dilations, because when you dilate something, you create a similar figure to it, just bigger or smaller. So we're going to do a lot of things with dilations today. Here's our goal, to identify similarity transformations to verify properties of similarity. All right. So let me start off with a recap of last section. All right, because we are doing stuff with this. So dilations, all the transformations we've studied so far before this dilation section produced images that were congruent to the original figures. Those are called rigid motions. Dilation is another type of transformation. However, it may change the size of the figure. Therefore, dilation is a similarity transformation. That's what we're talking about in this section. A dilation requires a center point and a scale factor. And the letter n usually represents the scale factor. The value of n determines whether the dilation is an enlargement or a reduction. So if it's an enlargement, it's a number bigger than 1. If it's being smaller, it's going to be a number smaller than 1, like 1/2 or 1/3. But the other thing with dilations is, typically if we do it on a coordinate plane, the center of dilation is going to be the origin, 0, 0 on the coordinate graph. So that's something to note. You can use a scale factor to make things larger or smaller, or a larger or smaller copy of the figure, and that's also going to make it similar to the original figure. So here's kind of what we talked about with dilations. You can kind of visually see it. Since there's a center of dilation, it's if let's say over on the picture, the point P is 6 units, whatever it is, away from C, then we're going to make it 6 more units. So it's 12 total. Okay, so it looks like we doubled it there. So it's when you're dilating something, it becomes that many times bigger, but also makes it that many times away from the center. Okay, so the important part to note here is the notation. So if you see a dilation, we use a little fancy parentheses, a little arrow parentheses here, and in it we include the scale factor first, and then the center of dilation. Okay, and then we also usually put the figure that we're dilating at the end. So if we're looking here, and we have example 1, we have triangle LMN with the vertices -4, 2. So I'm going to label it 1, 2, 3, 4, and 2. -3, -3. So that was M. And then -1, 1. There's our triangle. That would be N. Suppose the triangle is translated 4 units to the right and 2 units up, and then dilated by a scale factor of 0.5, with the center of dilation as the origin. Sketch the resulting image and the of the composition of transformations. So first of all, we're gonna state what this transformation rule is. We are going to do, remember when we do it, when we state the notation of composition of isometries, we use that little O in the middle for saying we're doing something of something else. So what we're first doing is actually what comes second. So we're first doing a translation, 4 units right, so it's a +4, 2 units up, so it's +2, and after we do that, we're doing a dilation of 0.5, and we're going to say the origin All right, so we're doing a dilation of a translation that we would have already done, and of course we can put um, of LMN. Okay, so let's do that. First, we're doing the translation. 4 units right and 2 units up. 1, 2, 3, 4, 2, 1, 2. Again, you can do this without 1, 2, 3, 4, 1, 2, without showing the graph, because you can do the math without it. However, we're going to do it with it right now. So there's after the translation. And then a dilation. So when we have those new points, we've got 0, 4. We've got negative 3, we've got 1, our m would now be, 1, negative 1. And then our n would be 3, 3, 3. So when we now do the dilation of 0.5, recall we multiply everything by 0.5. So our resulting points are all going to be half of what the originals were. So we're still having 0 and 2 then. So 0, 2. 1/2 and negative 1/2. You can kind of see they're all getting half the distance from the origin. And then 1.5 and 1.5, or 1.5, 1.5. And there it is. So it is a similar figure. It's moved, but it's also half the size. Okay, and we have to know how to do that rule, how to state that rule. Those are the important parts here. And that's pretty much a recap of last time, but it's also what we're doing in this section. Now, examples 2, it says we already have the two shapes, and we need to say what the composition of rigid motions and dilation that maps trapezoid ABC to MANHP. So now remember, we're starting at ABC and we're going to ABCD and we're going to MNHP. So what's happening? You can tell it's getting smaller. So it's going to have to be some sort of a dilation. And I can tell just by looking at a side that it's going to be half the size because this side is 4 and this side is 2. So I know it's going to be a dilation of 0.2, or sorry, 0.5, and we want it to be based on the origin. So let's see what we would have to do first. That could be first. Certainly could be first. Um, so based on the origin, and if we did that, then let's say we were, so we'd have right here, so it'd be half of them right there. It says negative 6 and 2, so it'd be negative 3 and 1. And then we have negative 8, negative 2, so half of that would be negative 4, negative 1. So there's our new trapezoid. And now, what's the other one? Well, it could be a couple things, but I think the easiest one, it looks like it just mirrors over to, yeah, it mirrors over the y-axis. So that would be a reflection over the y-axis. So that would be our composition of transformations here. We did a reflection after we did a dilation. Okay? All right, now let's recognize if things are similar or not. Two figures are similar if and only if there's a similarity transformation that maps one onto another. In other words, it's going to involve a dilation. Are the figures similar to the right here? Well, yes, they are. And there's two of them. There would be a dilation and a rotation. It does not necessarily matter which would come first. Either one could come first. We could rotate first and then dilate, or we could dilate and then rotate. Okay? Now, if we rotated first, this could be our center of rotation. Just rotate it that way. And then our dilation would be probably somewhere around here. All right. And I have one other picture. It must not have shown up on here. But let's just say we have, here's our second example. And I want to know if these figures are similar or not. So here we're going to do, let's do, whoops, a star. And we're going to we're going to transform that to this star. And the question that I have for you, are they similar? Are they similar or not? So take a second to maybe pause it and just think about it. What makes things similar? Um, and would this be categorized as similar shapes? So you can look at them and you can tell that they're congruent. They're definitely congruent. They have the same shape and same size. Similar, let's look up here. Similar, if two figures are similar, if and only if there's a similarity transformation that maps one figure onto another. There's debates both ways. Um, but if you say that they are similar, you'd have to have a scale factor for a dilation. And if you're saying the dilation, you could say a translation first. But then you can say a dilation of the scale factor would be 1. Okay? I'm not going to say where the origin is right now. But the scale factor would be 1. Because you can multiply them all by 1 and it won't change it. Some argue that that just means that they're congruent. They're not similar, they're congruent. Some would say that if it's similar, it has to have a scale factor of 1. I want to point that out to you that it could technically be considered similar since there would be a scale factor of 1. All right, so let's finish up by talking about if we are figuring out if something is similar or not. If there's a similarity transformation that we could use. It says, notice that the figures in problems 1 and 2 that we just kind of talked about appear to have the same shape but different sizes. Compositions of rigid motions and dilations map pre-images to similar images. For this reason, they are called similarity transformations. Similarity transformations give you another way to think about similarity. So in example 3, it says, is there a similarity transformation that maps triangle JKL to triangle RST? And here again, just like congruence, it's important to note the ones that are similar. The corresponding parts. So JKL, JK has to go with RS. Okay. KL has to go with ST. KL, ST. And then finally, JL with RT. So these two definitely look like they're similar. I would say they definitely look like they're similar. Maybe rotate them and then dilate them. But if you look at it, JK to RS, it got bigger. KL to ST, it also got bigger by a different amount. And then JL to RT, that also got bigger, but by the same amount as the other one. So if you think about it that way, logically, if it's getting bigger by a scale factor, the difference in their sizes would have to be different. It couldn't be 12 to 16, that's going up by 4, or it would be 1 and a third times bigger. 16 to 20 was also going up 4, but that would be 1 and a fourth times bigger. So there's not, it's going to be no, there's not a common scale factor. Okay? Not a common scale factor. If you look at the corresponding parts and the sizes of them, there's not a common scale factor between them. And that's really important to know when you're looking at similarity transformations. They have to have the same scale factor. Okay, let's just look at this real quickly. Triangle TUV at the right Give the vertices of a similar triangle after a similarity transformation that uses at least one rigid motion. So I'm going to let you do that one on your own. There are many, many different answers. You just have to involve one rigid motion and then a dilation that would make it a similarity transformation. But I'm going to then end it with these closing questions. I would like you to answer these. What do you know about corresponding sides and corresponding angles of figures that are mapped using a composition of rigid motions and dilations? Or, in other words, or similarity transformations. What do you know about their corresponding sides and angles? All right. And then number two, and actually back on number one, it is important to note there's a difference between how the corresponding sides and the angles. Um, but number two says, how can you show that two figures are similar based on what we talked about today? And that brings us back to our goal. I can identify similarity transformations to verify properties of similarity. Hope you have a good St. Patrick's Day if you are watching this on St. Patrick's Day. If not, why don't you enjoy the rest of your day, and we'll see you next time.